Robert and I went to graduate school together. Well, feels like a while ago now. I guess it wasn't so long ago. And I don't see your slide anymore, Robert.
Oh, yeah. Hold on.
He'll be speaking to us
Nope.
on something multiplicative and additive partitions, I believe.
It's coming. Oh, wait, just pause, hold it. Just like time is not elapsing right now. Okay, it's coming. Where was it? There it is. Okay. I just have to go through all of those steps I did before, but now I know what they are, so it's gonna be cool. Hey, is this a, are you seeing the screen? Okay, now I feel confident that I can begin a talk. Thank you for the nice introduction like 50 years ago before I did that journey through my operating system. It's so nice to see you all. Thank you for coming to the talk today. My name is Robert. It's such a great pleasure to see you. Many of you are my collaborators on the theorems in this very talk. And so you're just gonna have to bear with me, but you haven't seen all of it, okay? I also have to say that what I'm doing here is not a talk where I'm giving any proofs. I'm confident all of you have the skills that you could work out the proofs. What I am preaching here is a philosophy and sort of an overarching theory, okay? All right, and also a heuristic. Well, okay, let's jump into it. Let me go through a few steps here. I promise that'll work at the end of it, I think. And then automatically resize. Ooh, it's so nice. Okay. See, Larry, I got it to work in the LaTeX editor, despite all of your great advice, which I couldn't carry out in time. Cool. Okay, well, this is a talk about, as I said, I'm preaching a philosophy here. And the philosophy is sort of a unity of number theory. Well, oopsie, here we go. First of all, I want to talk about the two threads of number theory. The principal strains are kind of additive number theory and multiplicative number theory. On the additive number theory side, well, there are tons of well-known patterns and interconnections in the theory of partitions. Beautiful generating functions, really cool, surprising bijections. There are things like the Riemannian congruences and applications throughout the sciences and mathematics in combinatorics, algebra, quantum theory, and all sorts of other places. So partition theory, while it is quite a simple theory, the theory of addition, is also very deep in its connections. And so if the thing that I like as a partition theorist and a number theorist in general is I can be like, okay, how old is your subject? And you don't even have to say anything unless you're already in my subject, because I can be like, my subject's verifiably older. The first mathematical artifact, the earliest mathematical artifact that we have, is over 20,000 years old. It's the Ishango bone from Central Africa. Those little notches on there are, in some cases, are showing doubling or addition, multiplication and addition, and in other cases, they are prime numbers, and there's no other notches besides a prime number of notches or notches that seem to be showing addition and doubling. It's very fascinating. Of course, this is over 20,000 years old. We're interpreting it, looking at it as being a mathematical artifact. It's possible that it's random, but it seems really unlikely. There aren't very many random scratches on there. Like there are 0. That's another number. Okay, so in any event, I feel very proud to be able to claim a subject that has been going on for tens of thousands of years. It's such a long time. People just like us tens of thousands of years ago were asking the kinds of questions that we are. There are prime numbers on there. Okay, those were at least seen to be interesting. Here we have the Ahmose papyrus from Egypt. This is a very famous set of mathematical documents, also known as the Rhind papyrus. In any event, there's, for instance, the theory of Egyptian fractions is borne out on these. In order to do that, that's like partition theory for fractions. So it's like even harder. But I'm just saying, like the Egyptians had an amazing command of arithmetic. Here we have Kipu, which are these Incan kind of like string diagrams for writing numbers. These have been used for thousands of years. And essentially, this is a partition. Each of these strings, these strands, represents a number, and this is a base 10 numbering system tied in knots. And the red strands are like the size of the partition. They are the kind of like the sum of all of the strands in a certain region or across the whole rope. So these are used for counting and doing mathematics in Central and South America for thousands of years. These are partitions. That is an image of a partition just as much as a multi-set of numbers is. In contemporary times, comparatively, Leibniz appears to have been the first person to ask questions about partitions. He wondered what the size or how large the number of partitions P of n is for a given integer n. P of n is called the partition function, of course. We all know it and love it. And if you don't, then please, I invite you to do so. Euler, of course, really nailed down a lot of partition theory. The partition generating function is a very famous formula where it kind of gives the template for one of the ways we do modern partition theory. I mean, you see here the introduction of product sum generating functions, generating partitions on the left side from a product on the right. And the combinatorics in this case is encoded in the coefficients, in the exponents here of Q, of course, but also in the coefficients. We have two different kinds of sets of patterns going on and lots of interesting information that we can get about arithmetic from looking at these sorts of product sum formulas. This was also impressive because Euler connected analysis to partition theory. Here we have the discrete and the continuous kind of colliding and turning out to be in sympathy. Well, of course, the proof of this formula is that you expand the product on the right-hand side as a geometric series, right? And the n here is related to the index here. So it's q to the n, the geometric series, that's the variable. And then, of course, we want to rewrite the exponents here in terms of just the sum of these, of the integers n. That's just like second grade math. That's the proof. And then what we see here is that when we sum these up over all of the different n's that we can, make sums out of, each of these is a partition of each integer. That is, you pull a factor for each n, you pull q to some number, those multiply together, and when you expand them, you have the partitions. That gives you the left-hand side when you collect coefficients. On the other side of number theory, we have multiplicative number theory. And this is like, I think, what we think of as number theory. Like if you take number theory class, I guess from somebody besides us, then like you're likely to be thinking about the theory of primes, divisors, arithmetic functions, convolution, the zeta function, and that kind of business. And I'm thinking of that too. That's most of classical number theory. And if we want to trace the history of that, well, of course, there are prime numbers on the Ishango bone. I think if we wanted to skip forward in time a little bit, after the Amos papyrus, we could hit Greece. A lot of nice work was done in arithmetic in Greece, and it kind of caught on. So people have been doing arithmetic for thousands and thousands of years, and even little kids appear to totally love it because they do it every day. They must really love it. And again, when Euler comes on the scene, he really is a magical person. He was the first to understand the zeta function, which we call the Riemann zeta function now, of course. This object with the real part of s is greater than 1. And Euler was the first to compute explicit values. And he found, of course, that you could compute even powers of pi from using infinite series of unit fractions. So impressive. So for instance, he gave this family of values for the zeta function. Oh, they're so cool. I just want to look at them for a second. Oh, okay. Well, back to the talk. All right. So in any event, Euler also proved the product formula for the zeta function. And the Euler product formula says you can write the zeta function as this infinite product over primes. These are the primes down here. This is also really impressive. For one thing, it's the template for our entire study of L functions. There's an Euler product that generates the sum, and it connects analysis to prime numbers. Here we have infinite series, just really nailed down a generation before Euler's time. And he's connecting them to the prime numbers that go back to the Ishango bone. So incredibly cool. And so looking at these two, formulas of Euler's, the proofs kind of feel similar. On the left-hand side, you expand a geometric series, you collect the terms, and on the right-hand side, you get a sum over the integers. On the right-hand side, in each case, you have a sum over a really nice set, the integers. In the top equation, though, your coefficients are this hard-to-find sequence, the partition numbers. But it's easy to compute because on the left-hand side, the product is also over the integers. It's such a nice, easy sequence. The zeta function is a little harder. You have to take a product over primes. That's a pretty special sequence. But you get an easier sum on the right-hand side. You kind of know what the sum over the unit fractions is to some power. At least you know what that object looks like. We have two easy patterns and two complicated patterns, partition numbers, primes, and they are related really beautifully through these formulas. And again, I'm sort of hinting that the proofs feel similar, right? They kind of feel like the same, except for that the objects, the values, and the analysis are different. But besides that, they're the same. Well, now flashing forward into the contemporary era. In the 70s, Alati and Erdős, when Alati was just a teenager, used a bijection between integer factorizations and prime partitions. Okay, prime partitions are partitions where all the parts are prime numbers. You take those, you multiply them together, you have an integer. And every integer, you can split it into its prime factorization, and that's a prime partition. Every prime partition, you multiply the parts, you get an integer. So there's a bijection between them. And then they use this to study properties of arithmetic functions. It's very interesting because they're fusing ideas from partition theory and using them to study arithmetic functions in multiplicative number theory. Looking at their work, one wonders if there are other theorems in arithmetic where the theorems are images, in a sense, in the prime partitions, like in the Alati-Erdős sense, of other combinatorial or set-theoretic meta-structures. Are there larger structures that are like the invisible hand of number theory that are making all of these patterns work? In the 70s also, Andrews developed over a series of papers the theory of partition ideals. This is a really beautiful theory inspired by lattice theory, and it unifies many results on generating functions and bijections in a classical partition theory. It's also very interesting because it is an introduction of an algebra of partitions. And he's able to, using this algebra, build up a beautiful theory. And it kind of is suggestive of a universal algebra of partitions, just like we have an algebra in other mathematical fields. I don't mean fields technically, I mean in other mathematical realms. We have different kinds of arithmetics and algebras. One wonders, is there an algebra of partitions that generalizes arithmetic in the integers? The theorems of arithmetic we already have somehow make sense for partitions. Now by integers, we mean prime partitions in the sense of Alati-Erdős. Is there an algebra of partitions that generalizes arithmetic in the integers? That to me is a really inspiring question, and it inspired much of my PhD work and currently inspires much of my work. I think I'm chasing that question, even in my dreams. The philosophy of this talk then is that there exists multiplicative, there's a multiplication, a division, there are arithmetic functions on partitions, and these are the same exact forms that we study in multiplicative number theory, but translated into the theory of partitions. Another point is that objects in classical multiplicative number theory, such as those listed above, are actually special cases of partition-theoretic structures that are vastly more general. The theorems that we know are one out of an infinitude of like parallel number theories, the special case where we're just looking at prime partitions. Also, we expect arithmetic theorems from classical number theory to extend to partitions. We should be able to see new partition theorems coming from old number, or not old, they're always new, they're always fresh, but from classical number theoretic principles. And also, now this is a little more of an obscure point, but one might expect partition theoretic properties, special things like bijections and other weird stuff, Riemann congruences. Look, I don't know here, this is like kind of far out. We might expect these to somehow map back into the integers to give us weird bijections between subsets of integers. I've been working on this kind of thing in a current project with Madeline Dawsey and Matt Just, where we're looking at this kind of question. Okay, so here are a few notations. P is the set of partitions. We have the empty partition. Lambda is a multi-set of parts of the partition. They're ordered from left to right, going from greatest to least. P sub x, we're going to let x be a subset of natural numbers. Then this is the partitions into elements of that subset. This is a pretty big specialization of sets of partitions, but they lead to many well-known and nice theorems. Most of number theory that we think of on the additive and multiplicative side falls into this category. But notice that this is a really, really, really special condition on the set of partitions, that all their parts would come from the same subset of integers. So I'm just saying, like, number theory from this perspective is much broader than the types of structures we're looking at. For instance, here we have P sub the primes is the prime partitions. Backslash ELL is the length or number of parts. This is the multiplicity or the frequency of the particular part of a partition. Here we have the size or the sum of the parts, the thing that that the partition is a partition of. This notation means lambda is a partition of n. So for instance, if we were summing over these objects, this would mean the set of partitions of n. And on the empty partition, all of our statistics equals 0. Well, that's not exactly true, but of this set of statistics. Okay, so here I want to now move into the multiplicative theory that I'm trying to preach. We need to first start with a new partition statistic. Let n of lambda, the partition lambda, be the norm of lambda. The norm is the product of the parts. See, those are the parts from the previous definition. And on the empty partition, the norm is 1. It's an empty product. So in this case, it's not 0 like all of the other statistics, because those are additive statistics. This is a multiplicative theory. If you want more information, I want to see lots of cool different interpretations and stuff from both the literature and new theorems. You could check out this paper that I wrote with Drew Sills recently. It's on the archive, and in last year, it came out in Integers Proceedings. There's partition multiplication. This operation is basically the concatenation or multi-set union of the parts of a partition. So if we have two partitions, lambda and gamma, multiplying them means that we join their parts together and then I guess reorder them if you are writing them in this way. Cool? The identity is the empty partition. You multiply by that and it doesn't insert any new parts. And partitions into one part in this sense are like primes. Like these are each like the primes are to integer factorizations. So we get the fundamental theorem of arithmetic, for instance, and other structures from arithmetic. We also are defining a division of partitions. We will let delta divides lambda mean that all of the parts of partition delta are parts of lambda, like this. See, 3, 2, 1, those parts are all part of lambda. And we're going to let lambda divided by delta mean that you're just deleting the parts of delta from lambda, because delta is a divisor or subpartition of lambda, like this. Only 2 is left over. If you replace the partitions with just the prime partitions, if we specialize, then this specializes to multiplication and division in integers. Now here we have a parallel universe. Many objects from arithmetic have partition-theoretic counterparts. For instance, there's a partition-theoretic Möbius function. Here we go. Let mu sub p be 0 if the partition has any part repeated. That's just like if the partition is non-square, if a number is non-square free. And otherwise, it's -1 to the power of the length of the partition. And again, if you specialize to the prime partitions, then this partition-theoretic Möbius function specializes back to the classical Möbius function on the norm, the product of the parts.
Hey, Robert, can I ask one question?
Please do.
So with the division,
Walter.
Yeah, I was just wondering if it's useful to somehow formally, so partition lambda isn't divisible by any other partition, but have people looked at sort of formally adding in, sort of formally defining division of any two partitions and sort of making it into a field? Do you know anything about that?
So Ian Wagner and I worked on that some years ago when I was in graduate school. I've worked a lot on that kind of thing. I haven't published anything, and it's a totally open subject. No, I don't think that people are working on that. I've looked into that, and I'm really interested in it. I would love to send you my notes if you're interested. It's something that I think would be really interesting. That's more detailed than I've looked at that area yet, and it sounds like a really great idea. I would love to hear more about that if you work on it, and I'd love to talk about it if you're interested.
Yeah, just curious. Thanks.
Thank you, Walter. That's a great question. Thank you. So we have these two parallel universes of number theory. And we'll see that many objects from arithmetic have partition counterparts. Hold on. So as just like with sums over divisors, we have sums over subpartitions. And it looks just the same using the notations that we've set up here. And just like the classical case, the sum of the partition Möbius function over the subpartitions, like the partition divisors of lambda a partition, it acts just like the Möbius function. You can see it's the same theorem. We replace the empty partition, that replaces 1 in the conditions. We have partition Möbius inversion. I need to flash through these parts because I want to get to, there's so much more. Okay. So we have the same theorems, basically. This is the same Möbius inversion theorem, but these are partition-theoretic functions. They could be mapping into the complex numbers, or they could be mapping just from partitions to partitions. This is true very generally. Classically, we have that mu has a close companion in the phi function, of course. They're basically kind of like sibling functions. And we have the same sort of relationship in partition theory. For instance, as a partition phi function, which we define as the norm, the product of the parts, times the product of 1 minus 1 over the parts with no repetition. You see how this is very similar to the product definition of the phi function. Now notice that we don't have the interpretation of this, that it's counting the number of co-prime somethings up to something, because we don't have that kind of an ordering up to something on partitions. So in this case, this really is the natural way to look at the partition phi function. And given this definition, well, for one thing, this does actually reduce back to the classical phi function. And on the other hand, we get lots of the same classical identities, just like we saw with the Möbius function. But here we're replacing n either with a partition on one side or with the norm on the other side, where they would normally be the integer n or the divisor d in the classical functions. And there are lots of other things like this. Again, this reduces to the classical cases. The classical cases of these formulas are one out of infinitely many possible subsets P of partitions that this could be summed over. And so, if you reduce to the partitions with their parts in some other sets, you might get other nice structures that are like classical number theory, but also maybe different for those sets. Of course, you would get that. And there are also many other analogs of objects in multiplicative number theory. We have a Cauchy product formula. And notice that whereas on the left side, it looks like power series over partitions, on the right-hand side, it generates something that looks like Dirichlet convolution. And in fact, this is like F convolved with G in the partition-theoretic sense on the right. You see that we have the uniting here of the Cauchy product formula and the Dirichlet convolution product of Dirichlet series. If you swap order of summation in partition sums, you get the exact same formula, but using partition-theoretic sums and functions. And there are lots of other objects that generalize to partition theory. We have a class of partition zeta functions, for instance. These were the first things that I found along this line. I was trying to find a value of, I was trying to find a partition theoretic formula for pi day 5 years ago, because it was 31415. And so I thought it'd be really awesome to come up with a totally dank formula to post onto Facebook, and I did. And then when I showed it to my friends and my PhD advisor, Ken Ono, they're like, that kind of looks like a zeta function. And as I started to dig more into that, I was like, oh my gosh, the whole theory is here. In any event, a partition zeta function for a subset of partitions, a proper subset, is this sum. we're replacing a sum over the integers to the s power with a sum over the norms of partitions in this subset. Clearly, there are infinitely many of this object, however many possible subsets p prime there are of partitions. The analytic conditions depend on the subset.
Oh, sorry, Robert, we have one question.
Yes, please.
It says, can you repeat the definition of mu sub p?
Of course. Thank you for asking. Oh, sorry, that's not it. Here you go. So if the partition has any part repeated, then the mu vanishes. And otherwise, we're replacing the length of the partition with no repeated part with, in the classical case, the number of prime factors. So this is basically analogous to that. And then you'll see that it is the analogy. Is that cool?
Yeah, they said thanks.
Thank you. Let's see, where was I here? Oh yeah, okay. Here the norm, this is the norm of the partition inside the zeta function. And note that the if the empty partition is in the sum, its norm is 1. Now again, if we were to sum over partitions whose parts are all in a subset of natural numbers, right? Like all even partitions or all partitions who are 5 more than a multiple of 13 squared plus 1 or something. I mean, I'm just like saying like any subset of natural numbers, no matter how bizarre, we get Euler products. So this is why I was saying that this is where the theory really does connect nicely with the classical theories, and both in partition theory and in multiplicative number theory. However, again, this is much more general than just these kinds of cases. And we won't usually actually be looking at these cases for the rest of the talk. Okay, I just want to show you that this definition here, if we fix S, the argument, so that we can just see how different subsets change the values, we'll see it's really a function of both S and of the subset P. So for instance, here we go. If we sum over partitions into prime parts, that's the classical zeta function. It reduces to that in that case again. We get classical number theory when we make that particular specialization. If we sum over partitions into even parts, then you see that the zeta function gives pi over 2. This is pretty cool because we don't get from the Eulerian cases, we don't get like odd powers of pi. So here we have one.
We have another question.
Yes, hi.
About why we don't allow the full set of partitions in the definition of the partition zeta function.
I should have said that, and I'm sorry I didn't. Okay, thank you for asking that. Well, number one, let's look at the Euler product. If 1 is in the set, the subset X, then we have 1 minus 1 here, but it's 1 over 0. Number 2, for more general cases, let's imagine we allow partitions. Let's say that we imagine that we allow all of the partitions. Well, the partition 1, 1, 1, 1, 1, 1, 1, 1, 1, and so on. There are infinitely many partitions into all ones. Each of those has the norm 1. And so that contributes 1 plus 1 plus 1 plus 1 plus 1 and so on to the sum. And then it diverges. So that's 2 different ways of looking at it. You could let any subset that has a restricted maximum number of ones would be allowed. So for instance, if you allow partitions with up to 7 ones, you'll actually get 7 copies of the same zeta function. Every time all those ones come up, you'll get the same norm. Does that answer that question okay? Thank you for asking that. So now coming over here and looking at the evaluation where we look at the zeta function over partitions into distinct parts, that's a nice subset of partitions. Remember, we're fixing the 2 here, so we can really just look at the behavior of the zeta function when we switch the subsets. We get this hyperbolic sign of pi over pi. This is crazy too. I mean, it's not like totally crazy, except for that the hyperbolic sign of pi isn't really like a pertinent value of that function. So like it's a pretty cool formula. In fact, all of these are pretty cool formulas. And we get other formulas that are partition analogs of classical identities like these. These are identical to the classical cases, and they do reduce to the classical cases if we are looking at prime partitions again. The takeaway from all of this is that different subsets of partitions induce different zeta values, and that classical zeta function theorems give us new partition-theoretic theorems. One other thing I want to point out again, I know I'm just saying this over and over, but there are infinitely many cases of this theorem for every subset X of natural numbers. The subset X is the primes gives us the case that we're already familiar with. There are other cases. I don't know if they're all the same structure or if they're different. I haven't, that's kind of a big question, but in any event. This is pretty cool, but it'd be a lot cooler if we had families of identities like Euler's values, right? Pi to the something times a rational number. That's really awesome because you change the argument and you still have the same form. Those other cases don't come from theorems like that. You change the argument and you get different forms. So a question that one might ask then is, are there cases of partition zeta functions that are like this? So that for the right choice of the subset P prime, we actually get something like this. The partition zeta function, with argument n, some integer, is equal to pi to some power that's an integer times a rational number, just like the Eulerian cases. That would be really nice. And of course, we do have those. That's why I'm making a big deal about it. If you were to focus on the zeta function of partitions of fixed length, all the partitions with 5 parts, all the partitions with 100 parts, all the partitions with 1 part. So if you define a sum of partitions over fixed length, k, we let this zeta bracket s, k, be the partitions of the zeta function summing over partitions of length k. All partitions, not like a subset of natural numbers giving the parts. In this case, we have the same convergence condition as for the Riemann zeta function. In fact, it turns out that this is really closely related to the Riemann zeta function. Here, the zeta function where we're summing over partitions into k parts, and we're fixing the argument at 2, just like we did before. So this is in that same list I gave before. We fix the argument, but we change the subset, partitions into k parts. Then we see that it's actually a rational multiple of zeta of 2k. And it is pi to the 2k times a rational number. We do have a family. For every length of a partition k, fixed length, we have a zeta value that is related very closely to the classical case. And by the way, if you set k equals 0, you actually get the correct value from this equation of for solving for zeta of 0 that you get under analytic continuation, which is kind of cool because this is not involving analytic continuation. Now, looking at that, you might wonder, can we get more? For instance, can we take a different argument from 2? That was harder. My colleague, Larry, actually figured out how to do this using Fabio-Bruno's formula. And it turns out that, in fact, we do have for any even argument and partitions of any length k, a similar formula where we get a rational number times a power, an even power, because these are even numbers, of pi. So this is much broader than Euler's generalization. Remember, right here, we're able to solve for every single Eulerian value. And that's just for the s equals 2 case. So here we have every even number. We have infinity more of these formulas. Now, it turns out that other partition zeta functions, not these, can be analytically continued to the right half plane. And I just wanted to point out that that's an interesting result. And another, knowing that, another natural question is, in general, if we take the argument to be s a complex number, do we get other analytic properties that we like to look for in the zeta function? Continuation, what about the poles? What's going on with the roots? Those kinds of questions. Well, we do actually have a really nice general formula for this partition zeta function over partitions into a fixed lengths. Here we go. So the zeta, where the argument is s, but we're summing over partitions of fixed length k, k equals length 1, k equals all length 2 or something. That turns out to be explicitly written as a sum over the partitions of k. This is a finite number of partitions of this. It's basically a linear combination of zeta values with rational numbers as weights. This comes also, one way to prove it is from Fabio-Bruno's formula, of course. You could see that from the shape of it. It was not easy to prove, however, from Vanderbilt's formula. I'll tell you that. In fact, I couldn't. I failed to do it. I knew that it was true. I was having a walk one day at George Andrews's birthday conference, and I knew that it was true suddenly because the birds were singing and the sun was shining and there were flowers in the trees. I just knew that it was true. I was like, this is true. And I knew it for a whole year, and then I realized I needed to prove it, and I couldn't. And then I was deflated because I knew it wasn't true. And then Drew proved it using a much more complicated method than I could possibly have thought of. Drew Sills did. And it turned out it was true. It was really exciting and not disappointing, because it gives us lots of new information about these partition zeta functions. It kind of closes the book on this particular one, at least on those primitive questions you might ask. For instance, the left-hand side, the zeta function, inherits continuation from the zeta functions on the right-hand side. We get poles. We can identify that there are poles at the unit fractions up to 1 over k, this k, because that's where the poles of all of these are. And all of these have trivial roots if s is an even number. And so we have trivial roots also at the negative even integers, just like the analytic continuation of the classical zeta function. Of course, it inherits that from the classical zeta function because it can be as a linear combination. Yes.
Well, it was also sort of answered in the chat just now. There's a question about if we can rewrite this or connect this to multiple zeta values or multi-zeta functions.
That is a really great question. They multiple zeta values, I actually stole the notation from multiple zeta values for one thing, just you might have noticed that. And so multiple zeta values are some multiple zeta values are a subset. There's an intersection with certain partition zeta functions. But if we restrict to partitions into distinct parts, then we get multiple zeta values. But also it doesn't totally contain the theory of multiple zeta values. And I think that we addressed that in the paper with Larry and Ken a few years ago. This paper, that one, 2017, if you're interested to check it out. That's a really good question. There's a lot in that direction that I haven't looked at that I would really like to. I can see that there's a trail leading into something interesting that it looks like it would be a great idea to go down. Oh, and that is it for that particular formula. I want to note that we don't get zeros at the roots of the zeta function unless k is equal to 1. So this partition zeta function does not vanish on the 1/2 line. Because if one of these vanishes on the 1/2, well, it might vanish on the 1/2 line, but not at the same roots that the zeta function does. That's what I'm not trying to claim that it doesn't vanish on the 1/2 line, but it doesn't vanish at the same roots, because if any of these vanish, then other ones don't. The proof of this mimics Drew Sills' combinatorial proof of MacMahon's partial fraction decomposition formula. This is a really famous formula. I'm giving it here because it gives a cool correspondence. Actually, we don't want this formula, but I want to point out that it's cool. Here we have a generating function on the left. It generates partitions of length k, as well as largest part k. You can look at it both ways. And on the right, it is a very similar looking decomposition as a sum over partitions of k. Length k on the left, size k on the right. That's a cool correspondence. Actually, we don't want
length at most k on the left.
Thank you, Drew. Yes, yeah. This is where I was going with the next one. You're right, Drew. Thank you.
Yeah.
What we really want is to multiply that by q to the k, so that we insert a part of size k. So now we have, thank you very much, Drew. Now we have partitions of length k on the left, exactly k. That's because inserting a largest part k is the same under conjugation of inserting a length k. And that gives us this formula. It's basically the same formula. We just get these q's upstairs now. And I just want to point out, okay, hold on. I want to go past all of this proofy stuff because I want to point out that it's really similar looking to our formula for the zeta function. Look at it. See here, sum over partitions of length k, zeta sum over partitions of length k. See the geometric looking series, the zeta function looking series correspond. And on this side, we have this Fada-Bruno looking formula business. Fada-Bruno's formula looking business. That's the complicated phrase I was reaching for. Okay, there's a correspondence in the terms. Look at the zeta values or the zeta functions and look at the geometric series here. looking at those, we're seeing that there's a correspondence between the generating functions and the corresponding zeta function components. Here it is. This is just looking at that, at those formulas. So the question is, what does it mean? How is this an analogy? Well, in both cases, you're generating partitions in the same way. Here we're generating partitions by multiplication, see? And upstairs, we get the size by addition. Here we're generating partitions by multiplication, see? These are the analogous parts. We're multiplying them in the same way. And we generate the norm, the product of the parts of the same partition though. See, same partition up there as down here. And so noting that the correspondence is that in each case, we're generating partitions into a single part, any part, repeated j times. The geometric series here corresponds to n repeated j times, like we saw earlier. And this the zeta function also corresponds to n in the norm repeated j times, which gives you a j power. There's a duality here that says that geometric series and the zeta function with q to the j and n to the js as our variables or as our terms are interchangeable as generating functions for partitions of this shape. J repetitions of the same part. These are generated in the same way. I don't see these two objects as being different. They have different values. They have different behaviors in the complex plane. They are the same combinatorially. They're the same object, the geometric series and the zeta function from this perspective. Okay, there are a number of applications of this theory. However, I'm running out of time and I really want to get to one particular one. But I just want to point out that already we've seen projects in statistical physics, computational chemistry, as well as in pure number theory and combinatorics. And even the way that I first got into this kind of theory, which is that there are ways to compute pi using partitions, quite inefficiently to boot. For those of you that love inefficient algorithms, here you got tons of them. I'd like to go over one specific, really, really cool application that I worked on with my collaborators, Ken Ono and Ian Wagner. In fact, we are just submitting a second paper on this topic this week. This is on arithmetic densities of subsets of natural numbers. It turns out that we have partition-theoretic formulas for those, spoiler alert. So recall the arithmetic density of a subset of natural numbers. I don't know why I put z plus there. I think I maybe flip-flop throughout the talk. Is the limit of basically the number of numbers of integers in the set S up to n over n. If this limit exists, that's the arithmetic density of the subset. Now look, hey, I've got nothing against this beautiful definition of the arithmetic density, but I do want to say that it isn't the greatest because arithmetic density doesn't really have anything to do with the first n integers. Arithmetic density has everything to do with the integers that are not in this expression. The tail. You could chop off the first billions and billions and billions of terms, and it's not going to change the computation of the arithmetic density. So in my opinion, look, I'm just opining here. I'm not saying like trying to make any big claim, but I'm saying that in my opinion, this isn't it isn't a great definition because like, what if your set with positive arithmetic density, the first integer is so large that it could never be counted in the entire history of the universe. Like, let's say it's bigger than like a Google. So there's not enough Planck units of time since the birth of the universe that you could have counted that discretely, starting at 1. Even to get into that set would appear for all practical purposes in every possible way, but in an abstract definition to have density 0. I'm just saying the expression doesn't give you the elements of the set when you start counting at 1, because the density is happening far on down towards infinity. And so while this is a great definition because it's analysis and it allows us to use sequences, it's a little bit unsatisfactory. And there's another thing about it. Each of these integers in this up to n is counted with a 1. 1, 1, 1, 1. That's how you get the count of them. And what if you have the same number of elements in the set, but they're shuffled differently? They have different spacings between them and stuff. This also doesn't catch that. I mean, look, I'm not like complaining about it. It's beautiful. But I'm just saying this is like 1 plus 1 plus 1 plus 1 over 1 plus 1 plus 1 plus 1 plus 1. And the spacings of those ones aren't caught in this calculation. You might be like, so what's the deal? Why do you care about that? Okay, well, I believe that we might actually have a better way to think about it using Q series. Okay, so for example, of arithmetic densities, the integers mod t in any congruence class mod t have density 1 over t, right? Like there are 1/2 of the integers are even, 1/3 of the integers are 2 mod 3, and so on. And square-free integers, just as obviously, have density 6 over pi squared. I'm just joking. It's a pretty non-obvious fact. But these are well-known facts. And higher kth power-free integers also have densities related to 1 over zeta of k. So now the way you would compute this classically usually is, well, there are different ways to compute densities, but they usually go down by either using a partial sum or using an analytic object. So for instance, the Dirichlet density, this is more satisfying to me, because here we have all of the elements of a subset of primes represented. Each one is represented in the sum, all infinitely many of them. That feels good to me. Same down here, all of the primes are represented there. They're not just represented with ones. If you take some of the primes in the subset and replace them with other primes in the subset, this is going to be a different number up until you get to the limit. I'm just saying the number, the numerical evaluation of this before S, while S is in the right half plane, the numerical evaluation actually does kind of capture something about the structure of that set. Okay, if you delete a term, this is going to be a little smaller until S goes to 1, of course. And then we have this magical thing happen where like the whole thing blows up to infinity over infinity, and somehow all of those infinities cancel out in just the right way to give you the arithmetic density. That is crazy, but it's also really satisfying to me that at least all of the elements of the set are represented as we're taking the limit. So you don't have this issue where you won't see the first elements of the set ever. You see them in every single step of, as S approaches 1, you're always seeing those terms represented. Okay, so a couple of years ago, Ian and Ken and I wrote a paper following up on work of Eladi's. And we were able to make calculations like this. Here we have a sum over partitions whose smallest parts are in a particular subset. Here, the smallest parts are congruent to R mod T. This is the partition mu function. Here we have Q to the size of the partition. We put a minus sign in front, that has to be there. Just works out that way. And if you let Q approach 1, noticing that this should be diverging, just, you would think in your gut that it would be diverging, possibly. I don't know what you think, but that's what I think. It turns out that everything cancels out perfectly and you get the arithmetic density of the set, 1 over T. So this is a legit way to calculate 1 over T. You're like, well, I could just take 1 and divide it by T. Well, sure, but you could do it more complicatedly this way. That's why we do number theory, okay? I'm just joking, of course. Here, the smallest part is SM. I'm using a notation I think I lifted from Rob Rhodes. And this extends work of Eladi, as well as of Matty Dawsey, and who was extending Eladi's work into algebraic number theory. This is a partition-theoretic analog of these works. So here's another example. The arithmetic density of kth power-free integers can be computed from a sum over partitions whose smallest parts are kth power-free. Same thing, we weight it with partition Möbius function, and then we put a minus sign in front, and you can use this as another way to compute 1 over zeta of k. Now, of course, we don't know what 1 over zeta of k is if k is odd, but we can still compute it this way, and we can do it really, really slowly. But in any event, the proof isn't too hard. But I will say that it also is, it was impossibly hard before we knew it. And like, this gives us another partition zeta function connection. I just want to say that this is another interesting connection between partitions and the zeta function. They're very naturally connected across a number of different like paths. Really fast, I just want to flash forward to right now this week. like yesterday, I think, or maybe even today, we're finishing this paper. We're waiting just for a final table of computations that Drew is providing us, actually. And then, I mean, not waiting. I don't mean that it's waiting for that, Drew. I'm just saying that that'll be the last piece of the puzzle. We're able to prove a more general condition that for subsets of natural numbers with a certain analytic condition we call Q commensurate or Q commensurability. I don't know exactly what the noun is there, but in any event, I'll define that in a second. But for any subset that is basically amenable to Q series computations, that's what Q commensurate means, we can make a similar type of calculation. You take the same sum as before over the sum of over the partitions whose smallest parts are all in that subset. See, this is so interesting because we're controlling the subset, we're counting it by partitions with their smallest parts in it. There's infinitely many of those out of the much larger infinitude of all partitions. But somehow those infinitudes are in the same ratio as the arithmetic density. It's really crazy, but it's true. It is very, very hard to prove. Oh my gosh, we've been working on it for so many months. More generally, this next one looks kind of crazy, but there are even more generally, we can, involving more general partition theoretic business. We have sums like this. This is an example. The phi function here could be replaced with other functions. Essentially, we can pair partition theoretic functions with certain analytic conditions with arithmetic functions and get formulas like this. And that's partition convolution upstairs. That's the thing that came from the partition Cauchy product before, sum over the subpartitions with the mu function involved. It looks just the same as the classical case. The second formula here extends work of Wang, a very beautiful series of recent papers. To prove this, it requires really, we had to develop a whole new theory of Q series density computations based on something called the Q density statistic that we named. I don't know why this is down there. That's a typo. Sorry for that, internet viewers of the future. But in any event, here we have this object is called the Q density. Look, it's kind of like the arithmetic density, but it's a Q series over partitions whose smallest parts are in S, divided by partitions in whose this is it right here. In fact, hold on a second. Now I can make that even. In fact, this is not the actual format of it. Hang on. Oh, I lost my screen. I don't know what's going on here. Sharing is paused. Bring your video to the front. Resume share. Here we go. Nope, that's not doing it. I'm going to have to stop share and come back. I'm so sorry for this. This is a nice little intermission right here as we're coming up at the end of the talk. Okay. No, that didn't do it, did it? Oh my gosh. The internet's so tricky. Here we go. Oh, I'm just going to go ahead and keep the screen that way for the rest of the talk. Actually, this is wrong. It's supposed to be a regular geometric series with Q to the n over n in S over the geometric series Q to the n with n greater than or equal to 0. That's what this is supposed to be. And here it's supposed to be the geometric series where we're restricting n into the subset S. This is not these aren't supposed to be partition sums. I'm sorry, that was a copy and pasting error. This whole page is riddled with copy and pasting errors. They all collided on one page in my paper. I'm thankful for that. Okay, and you can see here we have a different set of correspondences. There's so many, they're bleeding off the page. Between natural numbers under this particular structure here. This is the least prime factor of n. This is the largest prime factor of n. Here we have the smallest part and the largest part of the partition. And we have these analogies between arithmetic objects and partition theoretic objects. And I'll say that all of this is following Aladi's lead. This is essentially an instance of an Aladi duality between subsets, the maximum and minimum elements of subsets in both cases. Or of multi-sets rather. There's a whole partition theoretic multiverse that that I'm trying to describe and to preach here. And just to summarize, the philosophy of my talk is that there exist analogies of all of arithmetic and objects from classical multiplicative number theory. We might expect to find new partition theorems, but also we expect that partition theorems are giving us the objects from classical multiplicative number theory. And also, we expect that even obscure properties of partitions are rippling through the integers with obscure properties. Look, I promise you that there are all of the same bijections and stuff that we're used to are happening in prime factorizations. They're just so weird and obscure, you would never think to look for them. But they're there under the same maps that we're talking about in this talk. This is a work in progress with many of my collaborators, as well as my son, and a number of graduate student and undergraduate student collaborators. And I invite you to join me if you're interested in this business. Thank you all so much for listening. And thank you very much to Vanderbilt for having me to speak in your seminar. It's great to see you all. That's the end of my talk.
All right, well, let's all thank Robert for a very beautiful talk.
Thank you.
We wish to have you in person.
Thank you so much.
Here in the future, maybe next year.
Thank you. I would love that. Thank you. Hey, it's great to see you all.
We don't live very far apart yet. It seems like it might as well be 10,000 miles at this point.
That's right, but it also might as well be next door.
Yeah.
Let's think of it the neighborhood half full. Does anybody have any thoughts or any questions? Hey, Hannah.
Hi.
Oh my gosh, I'm so happy to see all of you. Look at that. Hello, Jeff. Hello. Michael. Oh my gosh. Alexander. Hello. Oh, it's really great to see you all.
Hello, Robert.
I had one question. So you're showing that you can get these zeta values and kind of these classical zeta functions, maybe even some L functions of Dirichlet series out of this thing. Do you have any examples that kind of produce modular things? So like L functions of modular forms and their special values?
Okay, Sasha. So number one, this theory actually is the theory that this piece of the theory that I'm saying is part of a much larger superstructure that does encompass all Q series and things like that. And it does involve modular forms.
Okay.
Now, it doesn't necessarily contain the theory of modular forms, but there are tons of connections. And on the other hand, I haven't followed them in very much. But I think that, for instance, the thing that you're talking about, the connections between the coefficients of certain modular forms of their, Fourier expansions and the coefficients of Dirichlet series, and there's like a connection through like Euler products and that kind of stuff, like with the Riemannian tau function. That I think that's. Look, I mean, like, it feels obvious to me that that's there. Mm-hmm. But it also feels like it's like a miracle that it's there in the first place. Mm-hmm. And like, that is exactly the kind of thing that would be really, really great and a super high level thing to try to work out. but also it feels like it's definitely within reach. And I think, to my knowledge, it hasn't been worked out unless it's really literally been done by somebody probably in this room right now. And I'd love to talk about that more if you'd like. I could send you a couple of papers, Sasha.
Absolutely.
That relate
that would be great.
Modular forms. So this theory actually, actually I'm gonna go one more step. I noticed the theory of partition zeta functions. And then separately, I was working on something called the Q bracket of Bloch and Akunkoff, which is a statistical physics operator that gives quasi-modular forms. Mm-hmm. Yep. And I was actually in India with my wife on Christmas Day when I realized that the way to look at the Q bracket was to use the thing I had already worked out with zeta functions and I had no idea would relate. And it totally was able to give me a way to explicitly compute the Q bracket. And then when I saw that the arithmetic was the same and that the zeta functions and the Q series were the same. And it kind of like, it was like one of those, everything's connected kind of moments. But the fact is that the whole thing I just said, there's an equally strong Q series side of that. And an equally, and probably equally, what's the word, like poignant, like feeling that there could be a connection to the modular forms that you're talking about, just like there is that same kind of strong feeling that there could be connections to L functions in the classical way. It's a great question. I would love to hear more about that. In fact, I believe that many people in this room are interested in that kind of stuff. And I wish that I could introduce you all to each other because I know almost all of you. And I know that many of you would like to know each other. In fact, hey, really fast, would you graduate students who are here do this? Give me a thumbs up. I want you to all see each other. Okay, or recent graduate students, like early postdocs. Okay, okay. So all of you just notice who each other are because you're going to see each other again and again and again, okay? So, like these are those thumbs ups are your future friends. Or your current friends, obviously. Hey, Jeff, hello. How are you? It's so great to see you.
We have another question in the chat, Robert.
Okay, I'm looking at the chat.
What is the analog of the Riemann hypothesis?
I just want to say something really fast. I'm really excited, Jeff, that you're here. Another thing that like gave me a clue of all of this was your talk at LSU, where you
Winnie Lee's?
At Winnie Lee's birthday conference. That's right. I was trying to like remember. We've gone to so many birthday conferences in the last few years. But Winnie Lee's birthday conference, you gave an amazing talk, and I believe that it was on relations between multiple zeta values or something in that universe. And you gave all sorts of cool like combinations and stuff. It was like totally amazing and crazy, and not crazy in a bad way, crazy in the best possible way. Like how could it be true? And that sort of is one of the things. I just wanted to say thank you very much. You've done so much amazing work, and I referred to it a lot in my current math path. Thank you.
I'll cross again.
I hope so. Thank you. Does anybody have any other questions?
Yeah.
Hey,
so-
Rob. Oh, sorry.
Oh, I just wanted to say there was the question in the chat.
Sorry. I forgot about that. I'm so easily distracted here.
What's the analog of the Riemann hypothesis?
Oh, that's a really, really good question. I don't think I know an analog to the Riemann hypothesis. I don't think I know. I want to know that. I'm really curious. That's like, for instance, on the zeta function where we know about the analysis, it would be really great to know. I mean, that's a great question. It would be just to even know what the statement would be really interesting. Because again, it can't be the same zeros as the values that are, as the classical roots of the zeta function, the conjectural roots. I will say something. I have a paper that's been in progress for about a year, but I just haven't had time to finish it because I have a job. And also I've been working on 17 other papers. And so they're not looking at the real part of the roots, but looking at the imaginary parts of the roots. I have worked out a theory where you can, where those imaginary parts come up naturally for any partition zeta functions that have an Euler product. And in the case that it's the classical zeta function with the classical zeta Euler product, you can write down something that's very close within decimal places to the imaginary parts of the conjectural observed roots, or I guess proved roots of the zeta function, the first, say, some number of them. Something that is very close, like within a 10th place or a 100th place of the known values of the imaginary parts of the roots of the zeta function from partition-theoretic first principles. So it doesn't say anything about the imaginary part, it doesn't say anything about the real part, but the imaginary part of the zeros of the classical zeta function. You can construct a sequence of numbers that looks very much like that from first principles about partitions and the subset that their parts come from. So I don't know about the analog of the Riemann hypothesis, but I am very interested in the imaginary parts and their values. I'd love to talk about this stuff more. If anybody would like to email me, actually, I'm putting my email address down.
I guess we talked a little bit about analytic continuation and especially analytic continuations not existing when we could show that there was like an essential singularity of the function.
Oh, that's a great point.
But now that you have this work with Drew, writing this stuff in terms of products of zeta values, maybe we could like look again at the analytic continuation there and see if there's like some function. We could try to write down a functional equation for certain types of values. So maybe there would be certain examples of certain families where once you write it in terms of the new formulas you have with Drew, you could write down functional equations, and then the analog of Riemann hypothesis, the natural thing to do would be search for a functional equation and search for root numerically on the line of symmetry.
Oh, that's amazing. Yeah, as usual, Larry. Yeah, amazing. Yes, you're totally right. Okay, so I didn't think of that. We showed that a different class of zeta functions, this is in a paper with Ken that Larry and Ken and I wrote, in case anyone's interested. But like, we showed that a different class of zeta functions with over a different subset of partitions, it's not possible to continue them across the zero line. That there's a line of essential singularities there, and it's not possible for any zeta functions that in that particular class. So we do know about 2 different classes of zeta functions. We do know something about their analysis. And maybe even in both of those cases, at least on the domain that we understand them, maybe we could do what Larry said and try to write down functional equations. Certainly, we could construct those from what we know, and look at natural symmetries. I didn't think about all that until you both. It's a wonderful path for research. OMG, those are great ideas. OMG, please let's all work on that. Thank you. That's a wonderful idea.
Somebody else had a question a second ago.
Okay.
Yeah.
Looking up. Okay. Go on.
Hi, Rob. Thanks for the talk. It's Emily.
Oh, Emily, thank you.
Hi. So do you expect all like sufficiently nice classes of partitions to have similar nice representations on the other end of the partition zeta function?
Oh, I really don't know about that. I mean, that's like
rather most. I mean,
no, that's like the dream. The thing that you're asking is that's the philosophical dream of this whole thing, is that it works in a lot of cases. For me, it was like finding a needle in a haystack where you have to like hunt for the right cases, but there's infinitely many possibilities. And then once you find the right case, that's a whole infinite family. It would be great to be able to understand slightly more generally what kind of things you would want to look for to do that. That's the dream, Emily. That would be great if that's so far beyond what I can imagine being able to pull off that it seems like the kind of thing you could probably do.
Have you thanks. Have you found classes of partitions that don't seem to behave nicely and you're looking for nice examples? Like any some set of partitions that is combinatorially interesting normally.
Hey, that's a really good idea. Yeah, so that might actually be easier, is to find, but like for instance, we were able to find that partitions where you allow infinitely many ones, they fail to have a zeta function because of convergence. So maybe, but that's like the most heavy-handed example, but that kind of thing, maybe you could find that certain terms will do certain things analytically if you restrict the partition. Remembering that the zeta function in the denominators now, instead of the size, we're looking at the norm, the product of the parts. So the parts, your subset of partitions could be chosen. So the product of the parts does something interesting, and I don't know what, and then you could squeeze something out of that. That's definitely possible. That's how I did the other cases, but it still felt like a major achievement when I did it, and I was really surprised that it worked. I mean, look, I showed them to Ken, and Ken sent them to some of his friends, to one of his colleagues who came back and said it couldn't be true. And then the next day he wrote back and computed it, and it was true. And so Ken came to me and he was like, whoa, it could not be true. And then the next day he was like, no, it's okay, it's true. It's a little bit of a roller coaster ride.
Okay. And then
yeah.
Oh, go ahead. Oh,
yeah, please.
Okay, and then one more thing. I know we talked about it like 2 years ago, but have you considered restricting that norm at all and considering what happens analytically there? So restricting the norm to only consider the first like kth parts. I know we talked about it very briefly in 2018, but that feels like decades ago.
Actually, to me, at my age, it literally feels like a week ago. I can remember our walk in the light rain towards the banquet at the conference.
Very quickly became heavy rain.
Okay, oh yeah, that's right. In any event, yeah, those are really great questions. I'm working in that direction a little bit with Matty Dawsey and Matt Just, a graduate student at UGA. But it isn't exactly what you're saying, but I think that we're poking around in that direction a little bit. I think that it would probably be great to have you in the future on our conversations like that. In fact, Maddie and Emily, if you don't know each other already, please meet each other. Because
Madeline Dawsey?
Yes, Madeline Dawsey.
Okay.
Yeah. And your future collaborators, I hope.
Yeah, maybe. I am currently looking for PhD programs still, so we will see.
Okay. Well, let that not daunt you from your number theory progress. I doubt that it is.
All right. Again, thanks for the talk, Robert.
Thank you, Emily. You're awesome. It's great to see you.
Good to see you too.
Great question.
I have a quick question / hope. I don't know, just that you mentioned, before we had that some of these even values of some of these partition things are rational numbers times the appropriate powers of pi. I just wonder if everything is like 3, 3, 3, 3. Is it possible is it possible for any other such values to show that they're irrational, like Opry's proof?
Oh my
Like,
God.
of course, it's a dream to find other examples like that, and that hasn't really succeeded in proving that zeta of 5 or zeta of 7 is irrational. But maybe I just, as a very maybe naive hope, I wonder if any of the other ones we're writing down, they're not the main zeta ones people usually try these experiments, but if any of the other ones we're able to show are irrational by some computer search for some recurrent sequence that satisfies something, just as a
it's such a great idea, Larry.
It could be a computer experiment.
It's an incredible idea. That is an amazing idea. One thing that I'll say is that there's Euler's continued fraction formula, allows geometric or hypergeometric series to be written instantly. In fact, all infinite series, but in a natural way, geometric and hypergeometric type series to be written as a continued fraction. It's just instant. It's literally like sum equals continued fraction. And using continued fractions, I believe, is how Opry went about proving the irrationality of zeta of 3. Oh, and BTW, for graduate students, you should check out the paper on Opry by, oh my gosh, it's gonna take me a second to think of it. Horton? Did I spell this right?
In the Intelligencer, those papers you're referring to?
Yeah, I think so. It's the one, it was about the conference where Opry announces it. Oh, wait, hang on. Vanderporten is one. I don't know why I typed an H there, sorry. I don't think I'm spelling his name correctly. However, I am about to give the link to everybody because this is a paper that everyone should read. It's so incredibly great. Opry's proof. It's an incredibly great paper. And it's delightful reading. It's a report on the conference where Opry, I put it in the chat, and I'm just about to share screen really fast. This paper is in a really amazingly written, incredibly interesting, and also crash course in many of the methods of irrationality and using techniques that Opry used. This is a report that Vanderporten writes on having gone to the conference where Opry, and I don't know how to pronounce that correctly, I'm sorry for that, gives the announces his results, and then everybody goes off into groups and then they try to figure it out and talk about it and stuff. And this describes that. Look. The lecture tended to strengthen the view to rank disbelief. So this is like this conference. They it's like Opry, like it's like broken glass suddenly, and everybody's like, "What?" This is how I imagine it, and they all rush off and start trying to figure out about it, and working through his methods. It's a great paper. I really encourage everybody to work through it. I've worked through it, but I haven't worked through it enough. I need to spend about a year doing it. The methods in that paper, however, involve continued fractions. Continued fractions are tied through Euler's continued fraction formula to hypergeometric series, and those are tied to partitions. Everything that we're writing down, these partition zeta functions, are essentially hypergeometric. And so it could be, Larry, that if you went through that path, it could be that looking at irrationality that way might be good. For instance, how about if we look at irrationality using the formulas that Ian and Ken and I proved for 1 over zeta of 3, using Q series instead of using, and then we use Euler's continued fraction formula plus generating functions, something irrationality. I mean, that kind of thing, that could work. It works as a hand wavy story arc.
Yeah, I mean, any generalization of Opry's example would be a big deal. So
yeah, I mean, I think Jeff is like a historical expert on this kind of thing. Jeff, what do you think about that?
Well, you can explore it.
Does it sound like a direction that is non ill-fated?
Well, people thought when Opry did it that they were immediately going to go in there and they were going to do all the higher odd zeta values by the same method.
I see.
This method produces a series of rationals that are converged sufficiently fast well-spaced series that converge sufficiently fast to the number that you can get it. And the rate of convergence matters, and it's a constant. And if the constant is small enough, it works. And if the constant's too big, it doesn't work.
Oh,
So
Yeah.
that beta 5, you can run the analog of Vaporay's method. Looks just the same. And at the end, you compute this constant of the rate of convergence of this geometric series. And it's too slow.
oh, that's very interesting. So in
But-
that case, we wouldn't get it.
The crazy thing about G functions that there's this, it depends on each individual number you compute this constant. It seems to work on some of them and not on others.
Whoa.
And so the method's been stuck for 40 years. But these are Padé approximations to something. And then there's higher dimensional versions of that have proved things like one of zeta 5, 7, 9, or 11 is irrational, but we don't know which one. At least one is irrational.
That's right. I've heard of that. I think you told me that once before, actually. That's a crazy result. So we know one of them is irrational, but not which one?
Right, and then there are infinitely many that are irrational, but you don't know which one, because then there's a bigger block from 13 to something that will contain at least one that's irrational.
So it really is. So it depends on the constant, and the constant somehow depends on the number that's in the argument. Is a number theoretic function.
I mean, people have tried many different generalizations of the zeta of 3 argument. Fritz Beukers, Beukers, has written 3 different papers with 3 different methods that get the Apparay numbers as the limits of various things that allow you to get proofs for zeta of 3 by different methods.
I see, but so far it hasn't gone higher than 3, except for just an existence type of thing. It's so interesting.
Well,
yeah.
I mean, they're proving explicit numerical things with series. I don't know. I think the Q series idea and letting it go to 1, that hasn't been tried, but somehow you have to extract explicit approximates in there and prove that they give you rational numbers that are converging to this limiting number. And there's sufficiently good approximations. It's the rate of approximation that matters. Right?
Gosh,
it's hard to say.
Thank you.
As an approach, it's interesting. It's too soon to figure out what might happen with it.
God, it's such a great point, Jeff, because Q series converge really fast compared to sums over unit fractions. But on the other hand, we found that our series for things like 1 over pi or 1 over zeta converge really slowly, the ones with the Möbius function in there. So that's a really great clue, because certain techniques produce.
Well, I remember a new method, you have to integrate it with everything else that's known to see whether you can combine the pieces in a way where you get something new. Right?
Yeah,
you can't predict in advance when you found a new idea how far it's going to go.
Yep. Thank you. Yeah, you're right. Gosh, hey, that was really great. Thank you very much. The thing about the approximations that Aubrey's finding, I remember now, you're right, because don't you find that the convergence of the continued fractions somehow bound the number? Isn't that a theorem that a number is irrational? It has something to do with how it can be bounded by the convergence? And then you use, and then, oh my gosh, that reminds me, Jeff, thank you so much for all this amazing information. I've got so adding into the thing that I was saying before about Vanderpoorten's paper here, everybody. This paper also gives a great review of convergence acceleration. And those techniques would be really, really great for somebody to master in our social circle.
Very important to master that stuff.
Yeah.
Exploited as far as it could be.
I mean, oh my gosh. Jeff, thank you so much for all those great comments. And Larry, thank you for your incredibly great ideas for directions for research. And all of you, thank you very much. This is really exciting and lots of great information. Okay, so Sasha put a link down here for a paper of Francis Brown.
And Francis Brown does have some stuff about the relation of this to multiple zeta values as well, I believe, in a different paper.
Yeah, Francis has a lot of stuff on multi-zetas, but yeah, there's this great paper. It's irrationality proofs for zeta values, moduli spaces, and dinner parties. And there's a accompanying recorded talk you can find on YouTube. But he recovers all the known results using a method that's kind of similar to Apparay's proof, using kind of integrals on certain moduli spaces. But
Very interesting. Thank you, Sasha.
yeah.
Oh, there's a point. Somebody asked a question up here. Oh, if you replace primes by prime ideals, what can you get? That's a great question. I'm really interested to see if this structure maps over into algebraic number theory. It seems like it should, since we have classical number theory, and algebraic number theory exactly generalizes it. And then we have classical number theory, and this partition theory exactly generalizes it. But they're not like, are they the same? I don't think that they are. I think algebra and partition theory are different. I'm really interested in this. That's a great question. Who asked that? Abdul? Abdelmajid, is that right?
Yes. Hi, Robin.
Hey, thank you for your great question. That's amazing. Thank you. It's a great question.
Thank you for your stimulating talk. Thank you.
Thank you so much for your stimulating questions. It's great to have you. Thank you, all of you, for having me to your seminar.
Okay. Thank you.
Thank you. Have a great day. Thank you.
Yeah, and my point, Robert, about the a prie's, it may be very unlikely, but it's like what Freeman Dyson called pit lamping, I guess, which is like things that are high impact but require very little effort to try out. You know,
I see.
so
Like, why not try it?
you know, people can do computer experiments. It may not take long to do those computer experiments, and you know, you might either find it or not find it, and then that's the end. If it doesn't take much effort to search, and the potential impact is huge, his point was that even if the likelihood is lower, if the amount of time and effort it takes to do it is also low, and the impact is high, then you should do it.
Larry, I have I'm working with a number of graduate and undergraduate students in sort of a computational number theory group that I have going at UGA. And I have lots of talented programmers in different languages. And so it's possible that that we could ask somebody to make computations like that.
That's the best use of it, is have a student try some a student who has lots of time try some experiments. And you know, because Zagier did some searches for, I mean, people have done searches for these numbers, and Zagier described some of his searches for other sequences like the a priori ones, and he did a search space of like 1 billion or something, and there were maybe 12 examples that a few examples that he found or something. But
oh my gosh,
people have tried these searches before, so I just wonder, yeah,
I love the
computational project
research
either gives nothing or something big. But
Larry, can we talk more about this actually? Because I'd love to like write down all of these great ideas, and literally like we could, between us and our students and other people we know the program, we could try to over time look at everything, try everything.
Yeah,
like we have decades ahead of us of collaboration and hopefully and of good times. And so in the event, it seems that we should try every single possible thing that we could try, if it's what you're saying, where it could be a high impact and low strain.
Yeah. Well, Dyson gave the example of searching for life, and he said, well, you know, it may be most likely that Euler or Enceladus might be some of the most likely candidates for life in the solar system, but they're very difficult to search. You know, so like, you know, yeah, there's like liquid oceans that you can search, but you have to like drill through a mile of ice. So that's like really difficult. That's really difficult and expensive, and takes a long time to plan out, but it might be the highest likelihood. And he said, well, you know, if he thought about if there was light, or if there was life out by Pluto, then that life would have to have adapted to an extreme low light environment. And like animals in the dark, they would probably, if you shine light at them, they would, you know, reflect it back, like, you know, when you shine a light into the bush, and you see these animal eyes popping out. And so he said, well, you know, it's much cheaper to send a mission and shine some lights out, you know, in the outer solar system, and see if some life form reflects light back or not. That's a much cheaper thing, you know, to reach the liquid water with hydrocarbons in it or whatever. And the liquid ocean is probably more likely, but it's like 1 million times more expensive and difficult to do. So you should try you know, he said you should try the easier thing, even if it's less likely, because, you know, if it's a millionth the cost, and it can be done with today's technology with no modification, then you should just do it, you know, even if it's unlikely. So yeah,
That's really,
really nice Dysons.
It's a really great approach, and I love that. And thank you for bringing that up. And I love Freeman Dyson so much. He was so amazing.
He was. I was
passed away.
glad I got to see him speak a few times. Yeah.
You're really lucky.
Well, me and Robert Lemke Oliver and Marie, we all got in, and maybe a couple other people, a bunch of grad students at Emory got in a car and like to University of Florida to see Freeman speak.
Right.
So he was giving a Hurricane Sandy, like he was supposed to speak at the Ramanujan conference, but Hurricane Sandy delayed him, so he gave a special talk later on there. And so it was basically just the Florida professors and us grad students. But yeah, it's like a 5-hour drive or something, but we got up at like 3 a.m, drove all the way there, saw him give a couple talks, and then drove 5 hours back the night of. So
same night. That's
full
awesome.
day yeah.
Well,
Yeah.
cool. You packed a lot into that day.
Yeah.
Thank you all so much for coming to the talk. It's so nice to see you all. I miss seeing you all out there in the in our physical avatars. I'd like to mention, just in case anybody's interested, this is I'm putting here the archive link for my PhD dissertation. It kind of compiles a lot of that. And while it does pull together some papers with some of you, it also gives, especially in the introductory part, it gives a lot of philosophy. And also here's a paper with the paper that I mentioned that Drew and I wrote just recently that gives the analysis part. And also I'm going to put in here the paper that Ken and Larry and I wrote where we talk about the analysis as well. Trying to find it really fast. I'm sorry I didn't have it on file, but here we go. Explorations, and here's one more little link here. If anybody's interested in this, just to oh cool. Oh, thank you, Carlo. Thank you. It's great to see you. Thank you.
All right. And if there's no more questions, I think I'll stop the recording here.
Thank you for having me.